students, today we will discuss about electronic configuration. First of all, what is electronic configuration? Electronic configuration means how the electrons are arranged within an atom and within various orbitals. We know that there is a nucleus and there are some orbitals S, P, D, F, and the electrons are present in those orbitals. Now the question is, how are these electrons are distributed among different orbitals? So we'll discuss about this all in this video. Before starting with electronic configuration, let's have a brief look at quantum mechanical model of atom. According to the quantum mechanical model of atom, there are some energy levels present within atom. Electrons are present distributed among different energy levels. That first energy level n is equal to 1, second energy level n is equal to 2, third energy level n is equal to 3. These are represented by n, known as principal quantum number. Then these energy levels, or we can say shells, these shells have some subshells which are denoted by S, P, D, F and so on. These are subshells. Shells or energy levels contain these subshells. Now these subshells contain orbitals. S subshell contain one orbital, P subshell has 3 orbitals, D has 5 orbitals, and F has 7 orbitals, and so on. So the structure is, first of all, shells represented by principal quantum number, that is n. Then these shells contain subshell, which is represented by L, that is azimuthal quantum number. And then these subshells further contain orbitals. These small boxes are orbital. One orbital in S, 3 orbitals in P subshell, 5 orbitals in D, and then 7 orbitals in F. And electrons are present within these orbitals in this box. So first of all, how to write electronic configuration? If you have seen, electronic configuration is represented in this way. Just say 3s2 or 4p2 or 3d10. Now what are these? This number represent principal quantum number, it is shell, this one. After that, this S, P and D represents azimuthal quantum number, that is L. And then these numbers represent number of electrons present in them. So electronic configuration contains 3 parts. First is principal quantum number. For this, the principal quantum number is 3, that is this 3s2 represents that 2 electrons are present in s orbital, that is s subshell. These 2 electrons are present in orbital of s subshell of third shell. Third shell, s subshell, and 2 electrons are present. Okay. Now let's go back to our topic, that is electronic configuration. Now electronic configuration is a distribution of electrons among different orbitals or subshells within an atom. Now how to write the electronic configuration for a particular atom? Electronic configuration is followed, it depends on 3 main principles. We follow these 3 principles in order to write electronic configuration of any particular atom. Now what are these 3 principles? First of all is Abu principle. According to this principle, electrons are present in electrons enter the orbital of lower energy first. That means electrons are filled in the orbitals in according to their increasing order of energy. Okay, the orbital of lower energy will be filled first. After that, we will move to that orbital which is of higher energy. This is the increasing order of energy of the orbitals. Now, how to know about which orbital is of higher energy and which one is of lower energy? In order to find out that whether the particular orbital, that what is the order for filling electrons in terms of energy of orbitals, we'll use this rule, that is L plus N rules. L plus N rule means if we talk about particular 1s orbital, the value of N is, yes, 1. And what is L? L means this one, S. S stands for L is equal to 0. P stands for L is equal to 1. D stands for L is equal to 2. So, for 1s orbital, N is equal to 1 and L is equal to 0. So, N plus L is 1 plus 0, that is 1 for 1s orbital. If we talk about 2s orbital, it will be what? N is equal to 2 and again L is equal to 0. So it becomes N plus L, 2 plus 0, that is 2. Now N plus L value for 1s is 1 and for 2s is 2. So that orbital which is higher value for N plus L will be of higher energy. So 1s is of lower energy as compared to that of 2s. Now if we talk about 2p orbital, N is equal to 2 and L is equal to P, P stands for 1. So N plus L becomes 3 here. This one is of higher energy as compared to 2s. And now if we talk about 3p, it will be N is equal to 3 and L is equal to again 1. It becomes N plus L, or N plus N is equal to 4. So this means N plus that particular subscalar orbital which has higher value for N plus L will be of higher energy. Using this N plus L rule, we calculate the values of L plus N for each and for every orbital, and we compare those values in order to find out the order of energy. Now, what happens if the value of L plus N, that is N plus L value for two different orbitals is same, then how will we decide the priority? For example, if we see 3s orbital and then let's move to 2p. For 3s orbital, N is equal to 3 and S is equal to 0. For 2p orbital, N is equal to 2 and P is equal to, yes, 1. This one is 3 and this one is again 3. And what will we do in this case? We find that N plus L value is same for both 3s and 3p. So what will we do in this case? In this case, we will look at the principal quantum number, that is value of N. The one which has higher value of N will be of higher energy. So in this case, because N plus 1 value is same for both, so we will look at the value of N, and what we see, the value of N for 3s is greater than 2s, that's why then 2p, that's why 2p comes first and after that comes 3s in this order. This is a predefined order which we will use in order to write down the electronic configuration. First we'll fill 1s, then we'll move to 2s, then we'll move to 2p, then 3s, then 3p, then 4s, and so on using this particular order. So this was the Abu principle, according to which electron enters the orbital of lower energy first, and this energy is predicted using n plus L rule. The one which has lower value of n plus 1, n plus L will be of lower energy. But if the n plus L value is same for two or more orbitals, in that case we see the value of principal quantum number, that is n. The one which has lower value of principal quantum number will be of lower energy. That is for the same value of n plus 1, lower value of L only is filled first. The next principle is Pauli exclusive principle, according to which an orbital can have a maximum of 2 electrons only. We know that S subshell has 1 orbital, P has 3, while E has 5 orbitals. Electrons are present in these orbitals, but according to Pauli exclusive principle, a single orbital cannot have more than 2 electrons. It can have only a maximum of 2 electrons. It means 2 in this one. That means the S subshell can have a maximum of 2 electrons because it has only 1 orbital. P subshell has 3 orbitals, so it can have 6 electrons at max. Similarly, B subshell has 5 orbitals. One orbital can have 2 electrons, so it can have maximum of 10 electrons. So this was the Pauli exclusive principle, that a particular atom can have a particular orbital can have a maximum of 2 electrons only, and those 2 electrons should also be of opposite spin. And if one moves clockwise, another must move anti-clockwise. This half handed arrow upward represents clockwise motion, and this one represents anti-clockwise. Those two electrons which are present in the same orbital must be of opposite spin. Okay. Next is our Hund's rule of maximum multiplicity. This rule states that pairing of electrons in orbitals of the same subshell. We are talking about the orbitals of same subshell. That means these 3 are the orbitals of same subshell, P subshell. This is the orbital of this, and these 5 are the orbitals of D subshell. So we are talking about the orbitals of a particular subshell. I did this for this. Pairing of electrons in the orbitals of same subshell will not take place until each orbital is singly filled. What does this mean? That suppose we have an electronic configuration D5. It has, we know that there are 5 orbitals. 3. Now, how will we fill these 5 electrons in these 5 orbitals? We can do one thing. We know that a particular orbital cannot have more than 2 electrons, so one can do that. First fill this, then 1. But this is the wrong way. 2 to 5, but this is the wrong way. These orbitals will be filled according to Hund's rule, which states that pairing of electrons in orbitals of the same subshell, this pairing is this. It contains 2 electrons, that means these are paired, again paired, and this is single. But pairing of electrons in orbitals of same subshell will not take place until each of these subshell contain 1 electron. It means the correct order of filling is first fill all these 1, 1, 1, 1. And now, if we are left with more electrons, then the pairing will start. But here we have only 5, so we will 1 in each of the orbitals. Now, if the electronic configuration is 6, D6, in that case, first fill all the 5 electrons with all the 5 orbitals with single electron, 1, 1, 1, 1. Then these are only 5, but we have 1 more. Then the pairing will start. If we have D8, in that case, first fill all the 5 orbitals with 1 electron, then start the pairing from beginning. That means 5, then 6, then 7, then 8. Means it has 3 paired electrons, 3 paired orbitals, and 2 unpaired electrons. Similarly, if we have an electronic configuration of D4, oh sorry, not D4, let's take another example of not D, this time let's say P4. In that case, P subshell has, 3 orbitals. In that case, first fill each of these 3 orbitals by 1 electron. Now we are left with one more. There are 3 orbitals contain 1 electron, total of 3 electrons. All of these 3 orbitals are now singly filled. Now we can start pairing. So we'll start from here. So this is the correct order of filling orbitals. First of all, fill all the orbitals of a particular subshell with single electrons, and then if the electrons are left, start pairing. Pairing will not take place until all the orbitals of the same subshell contain single electron or singly. Okay, so these were the 3 rules which we follow. First is Abu principle that electrons enter the orbitals of lower energy first of lower energy, then that of higher, then the higher, then higher. That means orbitals are filled in order of their increasing energies, and the energy is decided using n+1 rule. And if 2 or more orbitals, different orbitals, have the same value of n+l, in that case the order or the priority is decided on the basis of value of n. The next one was Pauli exclusive principle, according to which an orbital can have a maximum of 2 electrons, and those 2 must also be of opposite spin. If one is clockwise, the another one should be anti-clockwise. Next one was Hund's rule of maximum multiplicity, according to which the pairing of electron will not start until all the orbitals of the same subshell are singly paired. Now, what are the way in which we can write electronic configurations? Let's say we talk about hydrogen, the simplest one. Atomic number of hydrogen is 1, z is equal to 1. That means it contains only 1 electron. First of all, fill the first one. The first is s orbital. It can contain a maximum of 2 electrons, but we have only 1, so we'll write it in the form of 1s1. Or there is another way to represent the electronic configuration. Just write the name of orbital, that is 1s orbital, and represent the orbital, and write the name of subshell, that is 1s subshell, and represent its orbital in the form of box. It contains only 1 orbital, so only 1 box, and there is only 1 electron in this orbital, so only 1 clockwise. The next one is helium. It contains 2 electrons, as the atomic number is 2. So there are 2, and we can fill a maximum of 2 electrons in the first orbital, so we will write it 1s2, or we can write it in this form 1s and in the orbital 2. Arrow, half-headed arrow, one is clockwise, another one is anti-clockwise. If we talk about lithium, lithium has 3 electrons, atomic number is 3. So we'll write what? First we'll fill 1s orbital. It can contain a maximum of 2 electrons. We fill the 2 electrons in 1s orbital, 1s. Now we are left with 1 more electron, so we'll move to the next one, that is 2s orbital. So electronic configuration will be 1s2 and 2s1. 2 electrons goes to 1s orbital subshell, and next one goes to 2s subshell. Or we can simply write it in the form of box also. First represent 1s subshell, and we represent its box in the its orbital in the form of box. Same the case with 2s orbital, and its 2s subshell and its orbital in the form of box. 2 electron goes to first subshell, that is 1s2, and then 1 is in 2s, that is 2s1. Or there is another way. If you see, we can simplify, or we can write the electronic configuration of a particular element in short form. Helium is a noble gas. So if we see, this part represents a noble gas configuration, that is configuration of helium. What was the electronic configuration of helium? That was 1s2. So we can represent this 1s part by helium, writing helium, just write helium. If we write helium, then yes, this much of electronic configuration, and the remaining one will be written in this form. Similarly, we talk about sodium, we can write it in this form: 1s2, then 2s2, after that 4, and we are remaining with 7 more. So 1s2, 2s2, 2p6, it becomes 6, 2, 2, that means 6, 2, 2, 10, but the total number of electrons are 11, so 1 more in 3s. So the electronic configuration is 1s2, 2s2, 2p6. Why 6? Because p subshell has 3 orbitals. Each orbital contains 2 electrons, so a total of 6 electrons. So 1s2, 2s2, 2p6, 3s1. Okay, 1s2, 2s2, 2p6, 3s1. This is the electronic configuration for sodium, but it can be simplified also. How? If you see this part, there are total of 2, 2, 4 and 6, 10 electrons. 10 electrons means neon, which is again a noble gas. What will be the configuration of neon? 1s2, 2s2, 2p6, because the atomic number is 10. So we can replace this part by neon and just write down the remaining part, that is 3s1. Now, there are some exceptions also. There is another principle according to which half filled and fully filled. There are 2 types of orbitals, 3 types of orbitals. One is full filled, another is half filled, and another is partially filled. What are these? We know that a d orbital can have a maximum of 10 electrons because it has 5 orbitals. So a d subshell can have a maximum of 10 electrons. So if it contains 10 electrons, we'll say it is fully filled. And if it contains exactly half number, that is 5 electrons, we'll say that it is half filled. And if it contains any other number between 5 and 10, that is 6, 7, 8 or 9, we will say that it is partially filled. Similarly, if you talk about S subshell can have a maximum of 2 electrons, so if it has 2, we will say it is full filled. If it contains 1 electrons, we will say it is half filled. And if it there is no condition of partial filling in case of s orbital. So if we talk about p, if we talk about p subshell, there are a maximum of 3 orbitals. So it can contain 6 electrons at max. So if it has 6 electrons, we'll say that it is fully filled. If it has 3 electrons, we'll say it is half filled. And if it contains 4 or 5 number of electrons, that means it is partially filled, or we can say 1, 2 also. So anything other than half filled and full filled is partially filled. So according to this rule, half filled and full filled orbitals are more stable as compared to partially filled. And actually the order is half filled, sorry, the most stable one is full filled orbital is the most stable one, followed by half filled orbital, followed by partially filled orbitals. The most stable one is that which is fully filled. Next one is half filled and then partially filled. Now let's understand this situation with the help of an example of copper. Copper, atomic number of copper is 29. So let's write down its electronic configuration. The first of all, 1s2, then 2s2, then 2p6, 3s2, 3p6, 4s2. Till now we have filled 20 electrons out of 29. 10, 20. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 we have left with 9 more, so those 9 will go in 3d orbital, 3d 9. So this is the electronic configuration of copper. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. We can replace this particular electronic configuration by argon because it is the configuration of argon. Argon is again a noble gas which contains 18 electrons, atomic number is 18. So we can replace this much, 2, 2, 6, 2 and 6, that means 18 electrons by argon, and we can write the remaining part, 4s2, 3d9. So this should be the electronic configuration of copper. But actually, according to this rule that half-filled and full-filled orbitals are more stable, this gets changed. How? If you see, 4s2 is a full-filled orbital which is stable, but if we talk about 3d9, it is partially filled orbital and it is just one short of being fulfilled. So what happens that one electron gets transferred from this to this and it becomes argon followed by 4s1 3d10. Now this 4s orbital is half, this was stable earlier because it was fully filled, now it is half filled, it is again stable because both half filled and full filled orbitals are stable, so there is no change in the stability of this 4s orbital. It was stable before also because it was fully filled, now it is stable now also because now it is half filled. In both cases it is stable. The difference is in this. Earlier it was partially filled with 9 electrons, it was unstable, but now it is also stable because of full-filled orbitals. One electron gets transferred from this to this and this increases the stability. Number of electrons are same, 29 and 29, but just one electron gets transferred from this to this. What happens that this remains again stable because it is half filled in this case and it was fulfilled in that case. In both the cases it is stable, but now the stability of d orbital gets increased because of fulfilling. So this was an exception of electronic configuration in which in general the expected configuration from this was this, but actual configuration what we see is argon 4s1 3d10. This is due to stability factor of half-filled and full-filled orbitals. So this was the way of writing electronic configuration, how we decide the electronic configuration of particular atom or element. I hope it is clear to you. Thank you.